Alright, so in the last video we went over undamped motion, which is like the damping constant c would equal 0. And this is our general form of our equation for spring problems. And when c equals 0, this would just go away. And we'd factor this out, mr squared plus k equals 0, and we'd always get r equals 0 plus or minus the square root of negative k over m. And the square root of a negative number would always be a square root of a negative number, and that would mean complex roots. So if c equals 0, you only have one case, which is complex roots. But as we're going to see in this video is when we have damped motion, which means there's like friction or air resistance, it's possible to get all three cases: distinct roots, repeated roots, complex roots. In this video, we're going to do complex roots again, but anyways, let's jump right into it. So just get rid of this, and it'll all make sense soon. But now that c doesn't equal 0, there is some damping. We will consider this cx prime. And if we plug in our equations, our constants, we get this equation. But one thing I want to point out is, I actually lied to you. Amplitude phase form for complex equations, you also have this e to the alpha t. But alpha was always going to be 0 because you have negative k over m, like the square root of that. It would be 0 plus or minus the square root of negative k over m, or I omega. Alpha would always be 0, and when this equals 0, that just goes away. But now that we do have some damping or some friction, a won't always equal 0. So, and if we did have distinct or repeated roots, you would just ignore that. But it would just be 1. Anyways, let's jump right into it. So we have 4r squared, just doing some factoring, plus 4r plus 25 equals 0. And, well, this doesn't factor nicely, so we're going to have negative b plus or minus the square root of b squared minus 4ac all over 2a. And this ends up equaling negative 4 all over a plus or minus the square root of negative 384. And this would just be negative 4 over 8 plus or minus I square root of 384 over 8. So our alpha is just negative 1/2, and our beta equals radical 384 over 8. And this also equals omega. So we found our omega, but as you know from the last video, we are not even close to finishing this. We might not have enough time in just one video, but I'm going to try my best. So we have our initial conditions, and we know we have complex roots. So let's find our constants, our c1 and c2, because that is essential for finding a and phi, which is actually all we need to find so far, but it's going to be a process. So x sub t equals, when we have complex roots, it's e to the alpha t times c1 cosine of omega t, well, we'll write beta for now, plus c2 sine of beta t. So, we know our omega we know our beta, we know our alpha, so let's just plug that in. E to the negative 1/2 t all times c1 cosine of radical 384 over 8t plus c2 sine of radical 384 over 8t. And so we can plug in one of our initial conditions, but for our second one, we're going to need to find the derivative. So let's do that right now. And I want to point out that we have two functions with t in it, so we are going to have to do some power rule. So we have an ugly derivative to compute, but it won't be too bad. So we're going to take the derivative of the first times the second, plus the derivative of the second times the first. So derivative of the first, e to the stuff, is just e to the stuff times the derivative of that stuff, a little bit of chain rule, times just the normal part, radical 384 over 8 times t plus c2 sine of radical 384 over 8 times t, all times that e to the negative 1/2 t times negative 1/2. Plus, we still have this power rule, this normally, so e to the negative 1/2 t times the derivative of the inside. And the derivative cosine is negative sine, so negative c1 sine of radical 384 over 8t times, we have the chain rule, so times another radical 384 over 8 plus derivative of sine is cosine, so c2 cosine of radical 384 over 8t times radical 384 over 8, all times that e to the negative 1/2 t. So let me just clean this part up. Just so we can find our initial conditions. We have our derivative function, we have our position function, or like our normal function. So now we can plug in our initial conditions and find C1 and C2. So let's do that. So our first condition is x of 0 equals negative 2. So negative 2 equals e to the 1/2, negative 1/2 times 0. So this actually just goes away, it's 1, times c1 cosine of, well, this times 0 is 0, cosine of 0, plus c2 sine of that times 0 is 0, and this just equals 1, and this is 0. So we're just left with negative 2 equals c1. So that was pretty easy. And, well, we have this long-ass function, and, well, it's the same process. We plug in our initial condition, but we just gotta be very diligent, very careful that we don't make any mistakes. So, e to the negative 1/2 times 0, you're used to this just canceling out to 1, but we had this chain rule right here, so negative 1/2 times 1. All times c1 cosine of that times 0 is just 0, plus c2 sine of that times 0 is 0, plus e to the negative 1/2 times 0. Now this just cancels out to 1, times negative, we have this chain rule, so negative 384 over 8 times c1 sine of that times 0 is 0, plus radical 384 over 8 times c2 times cosine of that times 0 is 0. So this ends up equaling 0 equals, follow me up here. This ends up equaling 0 equals negative 1/2 times 1. So negative 1/2 times c1 times cosine of 0 is just c1 times 1, which is just c1, plus c2 times sine of 0, which is just 0, then plus e to the negative 1/2 times 0 is just 1, so we can disregard that. We have a sine of 0 here, so that's just 0, plus radical 384 over 8 times c2. And well, we know c2 is just negative 1/2, so this right here is just 1. So we move the 1 to the other side, do some algebra, and get c2 equals negative 8 over radical 384. So we found our constants. It was a little tough, but we did do it. So now let's just find A and phi, and then we'll be done. So we have c1 equals negative 2, c2 equals negative 8 over radical 384. And, well, A is just defined as square root of c1 squared plus c2 squared equals the square root of negative 2 squared plus 8 over radical 384 squared, which equals the square root of 4 plus 64 over 384, which equals 2.04 roughly. So that is A. Now for phi equals tan inverse of c2 over c1. And, well, tan inverse of c2, negative 8, over radical 384, over c1, which is negative 2. And this equals about 0.2013 radians. Remember, this is phi is in radians. So that equals phi, and that equals A. But we're not done yet. We have one small little thing left. Remember that tan inverse has two conditions. It must be positive, and it has to be in the domain of negative pi over 2 to pi over 2. And, well, C1 and C2, remember, they're like cosine of phi, sine of phi. So C1 is like the x coordinate. If we have our unit circle, C1 is negative, so negative x. And C2 is negative y. So we're actually in quadrant 4. But negative pi over 2 to pi over 2 is on this side right here. So we're actually going to need to add pi to get it within the domain. And then it'll be positive and in the domain. So we actually need to add pi to phi, and we're almost out of time. So in the next video, we're going to finish this up, and then we're going to do an example with distinct or repeated roots. We'll see. I'll see you in the next video.